Bound for Jupiter, Galileo is the most complex planetary mission ever flown. Galileo will release a probe that will make the first descent into the Jovian atmosphere. At the Jet Propulsion Laboratory in Pasadena, planetary missions like Galileo are monitored around the clock. Here, scientists can tune in the murmurs of their experiments, talking to them from over 5 billion miles away. Today, Galileo will pass within 1,000 miles of an asteroid named Gaspra. It's the first such close encounter ever.
We are approaching, closest approach on my mark. 3, 2, 1, mark. The spacecraft has physically flown by the closest possible to the asteroid Gaspra.
A 12-mile-long chunk of rock in orbit around the sun, Gaspra bears the scars of smaller asteroids. Another generation of scientists and engineers now knows the thrill of a first close-up look at a new object in the skies.
Some people here at JPL have been working, it's old hat to them. They've been here for 20 years. You know, to me, it's still fresh. Everything I see, Gaspra encounter. I wish I was here for Voyager encounter. That would be great.
Rocket power allowed us to take the first steps into space. Brain power allowed greater strides. Uncounted scientific lifetimes have been spent reaching for the sky.
Why explore? Who cares? It doesn't have a short-term payoff. It's not going to affect, in general, the livelihoods of the people living right now. And worse yet, why should people give their lives to it? And the answer, I think, is that it's basically a manifestation of a search for immortality. If one is part of doing something in one's own lifetime, which is lasting, such as the first look at Mercury, the first look at Mars, the Voyager project to measure the outer planets, people will be responding to those results. They'll be reliving them to some extent, long after you're gone and forgotten.
There's no sure path to a lasting discovery. Chance often plays a part. Satellites revolutionized communications in the early 60s. By accident, they also set the stage for the century's greatest discoveries. This Bell Labs radio antenna was built to track the new communications satellites, but the signals were marred by an ever-present static. After ruling out all possible Earth-based sources of noise, physicists concluded that the static was the afterglow of the early universe. The antenna had accidentally tuned in the longest-running show of all time, the Big Bang. According to the Big Bang theory, the universe was once extremely hot, dense, and chaotic. Even light was stuck in a traffic jam of particles. As the universe expanded and cooled, light was suddenly set free. Today, just 3 degrees above absolute zero, this light, called the relic background radiation, is the signal picked up 15 billion years later by the Bell Labs antenna.
I would say one of the most important events in the history of thinking of mankind is the discovery of the 3-degree background in 1965. Because this discovery gave real reason to believe in the fact that we live in an historical universe. This is the moment where the community of physicists and astrophysicists decided that this idea of an eternal, unchanging universe was wrong.
The Bell Labs antenna took the temperature of the relic radiation in different directions. But everywhere the antenna pointed, the same 3 degrees was measured. Other aspects of the heavens are far from uniform. In this Smithsonian Astrophysical Observatory map of a part of the universe, each point is a galaxy. We have found that galaxies are not strewn at random. Instead, they are clustered as if they lay along vast ribbons. How did organization like this spring from the chaos of the early universe? Galaxies could have grown by the force of gravity drawing matter together, but only if gravity had something to grab onto, some kind of primordial seeds, slight variations in the density of stuff long ago. Big Bang Theory predicts just such seeds. If they exist, they should be detectable as temperature differences in the relic radiation. Physicist George Smoot has been in hot pursuit of these temperature variations for most of his career.
That's the image we published. We just need to change the scale so it looks just like the pictures. Hey, that's really beautiful.
The best view of the relic radiation is in the microwave part of the spectrum, best seen from space or very high altitudes. In 1983, Smoot and physicist Philip Lubin traveled to South America to launch a balloon that would lift a gondola full of instruments. Things didn't go exactly according to plan.
Unfortunately, in Brazil, they lost our balloon gondola in the jungle somewhere. And so the graduate student and I stayed behind and bought Brazilian air passes. We'd sit on opposite sides of the plane looking out, crisscrossing the country, trying to find out what happened to our payload. We did that for about a week.
Smoot saw nothing but tropical scenery. But 1 year later, a call from Brazil brought news the payload had been spotted. Residents of a remote village had discovered the tattered remains of the balloon, and scavengers had gotten to the instrument. One part was decorating the village bar. Another was used to repair the town's police radio. But the data tapes were recovered. Smoot's next study would come off with less intrigue. The Cosmic Background Explorer, or COBE, was launched in 1989.
Solid rocket boosters have been jettisoned on time. All events continue to look normal.
One instrument aboard this NASA satellite was designed by Smoot and his colleagues to search for temperature variations in the relic radiation.
To me, this is the golden age of cosmology. In fact, by golden age, it's all fairly recent, that it's all had to do with technology and the ability to build instruments and to make these observations. And going into space is the critical part. We've done the part you can do from the ground. We're now doing the part that you have to go into space for.
This is the biggest day of Smoot's career. He prepares to announce his team's first positive findings from COBE. Anticipation of COBE's results has physicists in an excited state.
First paper this morning will be cosmic microwave background anisotropy measurements. The speaker is George Smoot.
COBE did find the telltale temperature differences that earlier studies hadn't been able to see.
Here's what the microwave sky looks like.
By luck, COBE's instrument was just sensitive enough to see them.
I believe we've achieved a sensitivity that's about 10 to the minus 6 in terms of delta T over T.
Over the last year, the COBE team had pieced together millions of satellite measurements to find the missing link between the early, chaotic universe and the highly organized universe we see today. This map shows the temperature variations of the remote relic radiation. Red areas are 30 millionths of a degree warmer than average. Dark blue, the same sliver of a degree cooler. The result? A portrait of the universe in its infancy. These ghostly ripples, predicted by the Big Bang Theory but never before seen, are kin to the primordial seeds that grew into galaxies and galaxy clusters.